Welcome to my today's video. So today I'm going to be going through directional derivatives and differentiability. So with that said, if you're new here and you have not subscribed to my channel, please do subscribe and remember to like, comment and share the video. I'll definitely appreciate that. So with that said, let's get into today's topic. So the definition of a directional derivative is as follows. Let f be a function in R2 with an open subset D. If u is a unit vector, then the directional derivative of f at point AB in the direction of u is given by this formula over here, right? Provided that this limit exists, right? So I'm gonna explain this definition over here using the following example here, right? So in this example they say determine the directional derivative of f who is x squared minus 3x at point 1 and 2, right? So you see here they say that you can determine the directional derivative at a certain point AB, right? So in this case that point it's 1 and 2, right, in the direction of u, and u is given by this, and then they said interpret your answer, right? So we're gonna go ahead and apply directly this formula, right? And we have to find the limit of this in order to determine the actual directional derivative, right? So with that said, let's go on over here. So here now you're gonna have f1 plus this is u1 over here. You take u1 h, see, multiplied by h, comma b, b is over there, that's 2, plus h u2, u2 it's a half times h, so it becomes h over 2, minus f at AB, so f at AB, so it just becomes f of 1, 2, y. So where there is x, you substitute 1 plus square root of 3 over 2h over there, and where there's y, you put that, and then this is f at 1, 2, right? Then you just simplify that, and then it gives you this. And then this h, you just bring it down here, so you divide the top part by h, and then you're gonna get this. So now we do have that part, so what is left now is to find the limit of this, right? So now therefore the directional derivative of f at 1, 2 is given by taking the limit as h approaches 0 of this whole thing over there, which is equals to this over here, right? So taking the limit of this as h approaches 0, so you just put in 0 there, so this falls away, so you just left it the square root of 3 minus 3 over 2. So that is the directional derivative of f in the direction of u at point 1, 2, right? So to interpret this answer, what this means is that we are moving through the point 1, 2 in the direction of vector u at the rate of 3 square root of 3 minus 3 over 2. That's what that means there, right? And then over here I left an exercise if you feel like exercising this similar question. It's over here, but here you're gonna notice a little bit of difference, because here we have u pi over 3. So, and then I gave you a formula here of how you deal with u theta, right? So this is the formula if they give you an angle, right? So u theta is cos theta sine theta. So now this is your unit vector. So if they say d u pi over 3, so now you first find u pi over 3, so which means you put pi over 3 here and here, right? So you're gonna get your unit vector, and then your point, it's 1 2, right? And then you just follow the same thing that I did above with this example. You should get straight to the answer. It shouldn't really be a problem. So with that said, I'm gonna jump straight into differentiability. Right? So differentiability, let f be a function in R2 with domain D, which is in R2 on an open set. Then let A, B in D, and assume that the partial derivative of f do exist. Then for h and k not equals to 0, vector 0, then e of h of k given by this formula, right? Then we say that f is differentiable at point AB if the limit of the absolute value of e of h of k as hk approaches vector 0 is 0. So the first thing to do will be to first determine your e of h of k, right? You determine it and then you take its limit as hk approaches 0, right? And if your limit equals to 0, that means f is differentiable at point AB. If it's not, that means f is not differentiable. So if this is not equals to 0 here, that means f is not differentiable at point AB, right? But then if it is equals to 0, if the limit that you take of the absolute value of h of k as hk approaches 0, it's 0, then f is differentiable at point AB. So with that said, let's get into the example that I prepared for the differentiability. So the question says, determine whether or not f of xy equals to x plus y squared is differentiable at point 1 1. Right, so the first thing to do would be to find your partial derivatives, right? So you find the partial derivative of f with respect to x, so that just becomes 1 because y squared falls away, and the partial derivative with respect to y, it just becomes 2y, right? So now you find your e of hk, right? So you're just applying this formula, right? Remember your a, b is that point. In this case, that point is 1 1. So where there's a, it's 1 plus h comma 1 plus k minus f at 1 1 minus h, the partial derivative of x at 1 1, k, partial derivative of f at 1 1 over that. So you simplify that whole top part, you should get k squared, right? And the top part just remains like that. And now moving from here to here, I wrote what happened here, right? Because here you cannot just take the limit of this, because if you're going to take the limit as h and k approaches 0, the whole thing is going to be 0 over 0, right? Which we don't want to deal with that case. So the good thing here will be to like simplify the whole thing first, to try to get to like to a point where you can take the limit without having any issues, right? Of like having to deal with cases of infinite over infinity, 0 over 0, right? So you can note that the square root of h squared plus k squared is bigger than k squared, right? So this means that this whole thing will dissolve into this, because the square root of k squared is equals to the absolute value of k, right? So this is where it comes from. And then k squared over the absolute value of k just gives us k. So now having this, having e of hk less or equals to the absolute value of k, this means that e of h of k is bigger than 0, meaning it cannot be negative. So that means now it's between 0 and the absolute value of k, right? For all h and k not equals to 0, right? So now what follows, we use the squeeze theorem, right? Remember, we want to take the limit of the absolute value of e of hk, right? So we take the limit at the left side and the limit at the right side. So if we take the limit at the right side, the limit of k, of the absolute value of k, as hk approaches 0, you just get 0. And the limit on the left side, the limit of 0, as hk approaches 0, 0, it's just 0. So by the squeeze theorem, this means that the limit of the absolute value of e of h of k, it just becomes 0. So with that said, we can therefore conclude that f is differentiable at 0.11. Yes. So with that said, I did leave an example down here. You just follow the same procedure as how I explained it above. You should get to the answer without having any problems. So thank you for tuning in into my today's video. That will be all.